A peaceful crater lake can hide an enormous reservoir of invisible carbon dioxide beneath its motionless surface. Gradually, Lake Nyos lies within a volcanic region where deep geological processes continue feeding gas toward the surface. Carefully, its steep basin reaches more than 200 meters deep, creating space for strongly separated water layers. Carefully, tropical weather disturbs the upper lake, yet the deepest water can remain isolated for many years across layers. Temperature and dissolved minerals create stable density differences that resist complete mixing from top to bottom. Through monitoring, stable stratification behaves like invisible flooring, preventing ordinary circulation from reaching the deepest basin throughout the layered lake. Magmatic carbon dioxide enters through the lake floor and dissolves under intense pressure at depth throughout deep water. High pressure keeps carbon dioxide dissolved, much like gas trapped inside a sealed beverage bottle, within stratified water. Greater depth raises pressure and allows each liter of water to contain substantially more dissolved gas during darkness. The dangerous reservoir grows silently because dissolved carbon dioxide remains colorless and in mineral-rich deep water becomes heavier, strengthening the stratification that keeps the gas reservoir isolated inside volcanic lakes. Chemocline separates contrasting chemical layers and limits vertical transport across the lake. This model explains gas storage. Fresh inflow mainly affects shallow water, while the deep reservoir continues evolving independently below, across the surrounding valleys. New volcanic gas can accumulate near the bottom before slowly dispersing through the lower layer during controlled degassing. Years of quiet accumulation can bring deep water progressively closer to gas saturation. This system reveals basin behavior. Gas remains dissolved until falling pressure makes bubble formation energetically possible during upward movement within regional hazard systems. Once bubbles appear, expanding gas lowers water density and can drive faster ascent through positive feedback within valleys. An ascending bubble plume can pull additional deep water upward and magnify the original disturbance across steep valleys. All disturbances may fade when gas content, depth, or surrounding stratification cannot sustain runaway ascent across steep valleys. From above, a dangerously charged lake can look completely ordinary until internal stability suddenly fails within stratified water. Every upward meter reduces pressure, allowing dissolved carbon dioxide to leave solution more easily. Inside the crater basin, near saturation, even modest upward movement can begin separating gas from the surrounding water across the surrounding valleys. A landslide could disturb gas-rich water, although evidence for the actual trigger remains inconclusive. Within stratified water, cold inflow represents another proposed disturbance, capable of shifting the lake's delicate density structure within regional hazard systems. Wind alone usually affects shallow water, but exceptional conditions might interact with other destabilizing processes through sustained monitoring. Runaway ascent may also begin internally when gas loading approaches an unstable physical threshold inside the crater basin. Instance. The 1986 initiating event remains uncertain despite decades of field investigation and physical modeling.
As pressure drops, carbon dioxide expands from solution and creates rapidly growing bubbles. This structure sustains gas release.
Expanding gas sharply decreases bulk density, making the parcel more buoyant than neighboring water throughout the layered lake. Faster ascent pulls surrounding gas-rich water into the plume and strengthens the instability during carefully controlled operations. Each ascending bubble grows because external water pressure continues falling toward the surface. This structure sustains upward motion. Rising gas-rich water displaces upper layers and can generate waves against the crater walls across steep valleys. A limnic eruption is an explosive release of dissolved gas, not a volcanic fireball, throughout the layered lake. Once released, carbon dioxide forms an invisible atmospheric cloud rather than remaining within the water across steep valleys. Positive feedback sustains the eruption until accessible gas-rich layers become substantially depleted. This mechanism sustains upward motion. The eruption overturns stratification and mixes water masses that were previously isolated. This mechanism steadily accelerates upward motion. Large internal displacement can produce waves even though no tectonic explosion occurs. This response steadily amplifies bubble expansion. Gas release declines after the most concentrated reservoir has vented into the atmosphere. This response amplifies bubble expansion. The visible water disturbance ends before the atmospheric hazard has finished moving downhill. This pattern sustains bubble expansion. On an August evening in 1986, communities surrounding Lake Nyos had no warning of the approaching hazard. Locally, witness accounts later described unusual lake noise, mist, and turbulent water during the event throughout the layered lake. Released carbon dioxide crossed the crater edge and entered valleys surrounding the lake. This response channels local danger. Because carbon dioxide is denser than air, the cloud preferentially followed low terrain downhill through modern scientific monitoring. The cloud did not poison through combustion. It displaced oxygen needed for breathing. This pattern shapes ground exposure.
Many residents were asleep or indoors when breathable air disappeared around their homes. This pattern concentrates local danger.
Elevation strongly influenced exposure because dense gas accumulated most deeply along valley floors. This model extends local danger. Topography created sharp differences between severely affected low areas and nearby elevated locations. This mechanism displaces local danger. Large released volumes allowed dangerous carbon dioxide concentrations to travel far beyond the crater, within regional hazard systems. Morning mixing gradually diluted the gas, revealing the scale of the overnight disaster. This process governs air displacement. Responders initially faced an unfamiliar disaster with no visible fire, lava, or toxic residue across the surrounding valleys. Water sampling soon revealed extraordinary carbon dioxide concentrations in the deep lake. This structure steadily shapes gas dispersal. Measurements confirmed that the gas originated from deep dissolved storage rather than surface decomposition through modern scientific monitoring. Chemical evidence linked much of the carbon dioxide to deep geological input. This response steadily shapes ground exposure. A smaller fatal gas release had occurred at nearby Lake Monoon 2 years earlier, inside the crater basin. The two disasters established limnic eruptions as a distinct natural hazard. This atmosphere pattern steadily channels ground exposure. Most lakes overturn regularly, preventing dissolved gas from accumulating to comparable dangerous levels. This pattern governs ground exposure. Rare combinations of depth, stratification, and continuing gas supply created the Cameroonian killer lakes across the surrounding valleys. Scientific explanation does not diminish the human tragedy caused by the invisible release. This mechanism governs air displacement. Reconstructing the mechanism became essential for preventing another disaster at the same lakes. This mechanism shapes downhill flow. The eruption resembles uncapping a pressurized drink, except the lake itself becomes the rising container through sustained monitoring.
Pressurization converts dissolved carbon dioxide into a separate gas phase, occupying much greater volume inside the crater basin.
Bubble volume changes buoyancy much more strongly than the small upward displacement that started the process during darkness. Each step reinforces the next, producing a self-amplifying eruption once instability becomes strong enough. Through sustained monitoring, trainment expands the eruption beyond the first disturbed volume and recruits additional dissolved gas throughout the layered lake. Near the surface, expansion becomes explosive because pressure has fallen dramatically from bottom conditions across the surrounding valleys. Water may rise forcefully, even though the primary released energy comes from expanding dissolved gas. Through sustained monitoring, rapid displacement can generate destructive water movement alongside the invisible atmospheric hazard. This response steadily reveals risk patterns. Pure carbon dioxide is colorless, so visible mist would come from condensed water or suspended droplets. Through monitoring, molecular mass makes concentrated carbon dioxide heavier than the surrounding atmosphere under similar conditions. During carefully controlled operations, gravity drives the gas cloud downhill like an invisible fluid following topographic lows. This mechanism clarifies risk patterns. Atmospheric turbulence gradually dilutes the cloud, but calm nighttime conditions can preserve dangerous concentrations inside the crater basin. Stable nighttime air can suppress vertical mixing and extend ground-level exposure. This response steadily constrains eruption dynamics. Complex terrain channels dense gas unevenly, creating sharp local differences in concentration. This structure steadily reveals hazard duration. Breathing becomes impossible when the cloud displaces enough oxygen from the surrounding air. This system reveals cloud behavior. Extinguished flames later provided evidence that oxygen had been displaced rather than chemically poisoned. Through modern scientific monitoring, open terrain and stronger airflow promote dilution more effectively than sheltered valleys. This response steadily connects feedback strength. Daytime heating increases atmospheric mixing and helps remove dense carbon dioxide from low areas. Through modern scientific monitoring, disaster required a chain of geological, aquatic, and atmospheric processes acting together. This structure explains risk patterns. Preventing currents required engineers to drain the invisible reservoir without destabilizing the lake again within regional hazard systems. Engineers designed pipes that lift deep water upward and release carbon dioxide gradually at the surface, at depth.
Initial pumping raises gas-rich water until falling pressure begins producing bubbles inside the pipe during controlled degassing. Once degassing starts, bubble buoyancy creates a self-sustaining fountain powered by the lake's own gas. At depth, surface release spreads gas safely enough for atmospheric mixing instead of sudden valley-scale accumulation throughout deep water. Continuous operation gradually lowers the stored gas inventory within the deepest lake layers. This model reduces deep chemistry.
Additional pipes increased removal capacity and accelerated reduction of the hazardous reservoir. This system steadily maintains stored gas. Long-term measurements documented major carbon dioxide reduction after sustained controlled degassing. This pattern steadily controls deep chemistry.
Changing stratification affects which water the system taps and how efficiently gas remains removable within regional hazard systems.
Repeated depth profiles track density, chemistry, and dissolved gas before dangerous conditions can redevelop throughout the layered lake. Chemical analysis distinguishes magmatic input, biological processes, and changes caused by degassing operations. This model supports stored gas. Accurate basin geometry improves estimates of stored gas volume and possible flow pathways. This network reduces early warning.
Degassing must reduce pressure without causing harmful mixing across the entire water column. This model tracks deep chemistry.
Bay's flow behavior changes as dissolved carbon dioxide concentration and intake conditions evolve during carefully controlled operations. Declining fountain strength can indicate successful removal rather than equipment failure alone. This process steadily maintains early warning.
Engineers applied similar controlled release principles at Lake Monaun after its earlier disaster. This response tracks early warning. Continued geological input means monitoring cannot end simply because stored gas has fallen. This response supports lasting stability.
Lake level and dam stability create additional risks distinct from limnic eruption mechanics. This mechanism maintains stored gas. Prepared routes and awareness can reduce exposure if instruments detect renewed gas release. This response maintains stored gas. Technology reduces danger most effectively when engineering, monitoring, and local preparedness operate together. This system reduces stored gas. Lake Kivu stores enormous quantities of carbon dioxide and methane within a complex stratified water column during darkness.
Strong salinity gradients help isolate deep gas-bearing water from the oxygenated surface zone during carefully controlled operations.
Lake Kivu differs from Nyos because biological methane production adds energy potential and additional millions of people live near Lake Kivu, making careful risk assessment exceptionally important. This response supports model accuracy. Methane extraction can produce energy while reducing stored gas when operations preserve lake stability through modern scientific monitoring. Safe extraction requires managing every fluid stream without weakening the lake's protective density structure during carefully controlled operations. Poorly placed discharge could mix layers or move dissolved gases toward more vulnerable depths inside the crater basin. Engineering designs aim to maintain stratification while removing commercially useful methane from deep water through modern scientific monitoring. Researchers continue debating long-term gas trends because methods, locations, and dates differ among surveys inside volcanic lakes. Some modern analyses find gas concentrations closer to steady state than earlier alarming projections suggested through sustained monitoring. The East African Rift adds volcanic, seismic, and landslide hazards that require integrated monitoring during carefully controlled operations. A possible trigger does not guarantee runaway degassing when the water column remains physically stable within stratified water. Forecasting require understanding how much mixing would overcome Kivu's strong density gradients. This mechanism steadily constrains regional planning.
Continuous observations can reveal gradual changes before they become dangerous or disrupt extraction operations throughout the layered lake.
Remote sensing adds regional context that underwater instruments cannot provide alone. This extraction system steadily improves risk assessment.
The lakes share core physics while differing greatly in size, chemistry, population exposure, and management. Inside volcanic lakes,
Researchers search geological records for evidence that similar gas bursts occurred elsewhere in the past, within stratified water.
Paleolimnology can extend hazard histories beyond written records, although interpretation remains challenging.
Limnic eruptions emerge from ordinary physical processes, combined in an exceptionally dangerous configuration.
The lake's silence is no longer mysterious because science revealed the hidden reservoir and learned to release it.
Some spiders leave the ground by releasing silk into the atmosphere. Their journey can extend far beyond the height of nearby vegetation.
Sailors reported airborne spiders far from land, centuries before modern experiments.
Early naturalists struggled to explain how wingless animals reached ships at sea. Ballooning does not require wings. Spiders manufacture their own aerial material from abdominal spinnerets. Different silk lines can serve safety, anchoring, and dispersal. Many spiderlings climb exposed surfaces before attempting flight.
Launch begins with careful sampling of local conditions.
Excessive wind can make takeoff too dangerous.
Ballooning often begins under relatively light winds.
Air near vegetation moves differently from air higher above.
Elevation gives the spider access to stronger transport forces.
The spider adopts a distinctive posture before releasing ballooning silk.
Fresh silk begins extending into the surrounding air.
A drag line can prevent an uncontrolled departure.
Takeoff occurs only after the upward force exceeds body weight.
Many launch attempts end without flight.
Still air observations revealed that wind could not explain every takeoff.
Researchers tested another force already present throughout the atmosphere.
Earth's atmosphere carries a natural vertical electric field.
Under fair weather, voltage changes continuously with height. Thunderstorms help maintain a planet-wide electrical system. Electrical forces exist even during calm weather.
Weather can modify the atmospheric field dramatically. Ballooning decisions occur within a changing electrical environment.
Pointed vegetation can intensify the local field.
Ballooning silk can carry electric charge. Like charged strands repel and spread apart.
Electrostatic repulsion helps maintain a broad lifting structure.
Controlled chambers isolated electric effects from aerodynamic lift.
Without the applied field, takeoff behavior remained limited.
Activating the field increased ballooning behavior.
Electricity stimulated silk release.
Electrostatic force produced upward motion in near-still air. Changing the field altered the spider's movement. Coulomb force can oppose the spider's weight.
Only a small electric charge is needed for a very light animal.
Exactly how ballooning silk acquires charge remains under study.
Charge mobility along fresh silk may influence its lifting behavior. Charged silk converts the atmospheric field into upward force. More charge produces stronger electrical force within the same field. Body mass strongly affects whether electrostatic lift is sufficient.
Smaller spiders gain the greatest advantage from low weight. Larger ballooners often release numerous fine fibers.
Longer silk can increase both aerodynamic drag and electrical force.
Ballooning lines can form complex multi-thread structures. Multiple fibers may spread into a broad conical fan.
Mutual repulsion reduces tangling among neighboring threads.
Electrical spacing can improve the effectiveness of the silk array.
Natural ballooning usually combines electricity with moving air.
Electric force can support lift, while wind carries the spider horizontally. Warm ground can generate rising air that extends flight.
Updrafts provide additional vertical motion.
Turbulence can create both opportunities and instability.
Moderate conditions are generally safer for launch.
Ballooning often peaks during favorable weather windows.
Solar heating can improve atmospheric lift.
Spiders wait for combinations of cues rather than one signal.
Special sensory hairs help detect the electrical environment.
Trichobothria are extremely sensitive mechanosensory hairs. They normally detect minute air movements.
Electric fields can also move these hairs.
The hairs respond mechanically to atmospheric electricity.
Laser measurements recorded electric field-induced vibration.
Mechanical responses differed across stimulus conditions.
Hair motion can become information used by the spider. Electrical sensing can influence launch behavior.
spiders respond before leaving the surface.
Changing fields can alter readiness to launch.
Behavior can track the electrical stimulus repeatedly.
Experimental effects were observed across multiple individuals. Sensing and physical force are related but distinct findings.
One system helps choose when to launch. Another helps produce motion.
Controlled experiments reveal cause and effect more clearly than field observations. Natural conditions are far more complex.
A spider likely integrates several sensory inputs.
Aerial electric sensing occurs elsewhere among arthropods.
Electricity can carry biologically useful information through air.
Ballooning joins a growing field of aerial electroreception. Ballooning is a dispersal behavior rather than powered flight. Many journeys are short. Even modest flights can cross barriers difficult to walk through.
Aerial dispersal can bridge water channels.
Some spiders reach remarkable heights.
Researchers have collected spiders far above the ground.
Ballooning can carry spiders beyond shorelines.
Spiders often arrive early on isolated young land.
A successful arrival can found a new population. Ballooning shapes population connectivity and evolution.
Dispersal helps spiders recolonize disturbed habitats.
Their arrival can influence agricultural food webs. Flight allows escape from deteriorating local conditions.
Crowding can favor dispersal. Food shortage may also increase departure behavior. Ballooning can relocate individuals toward better conditions.
Young spiders commonly disperse soon after emergence. Adults of some species balloon as well.
Body size changes the required silk configuration.
Successful takeoff depends on several interacting variables. Wind and electricity can contribute simultaneously. Electrical force mainly acts along the field direction. Airflow controls much of the sideways journey.
Updrafts and charge can reinforce one another.
Atmospheric conditions reshape both forces.
Strong electrical fields do not guarantee safe flight. Ballooning requires tolerable mechanical conditions. Spiders appear to choose balanced launch windows.
Their nervous system integrates several environmental cues.
Behavior places the animal where physical forces are strongest.
Physics models test which force combinations can reproduce observed flight. Charge location along silk affects predicted motion.
Different electrical arrangements can generate similar takeoff behavior. Directly measuring charge on airborne silk remains difficult.
Wild studies must monitor many variables at once.
Improved imaging can resolve the first moments of launch.
Tracking tiny ballooners over long distances is still a major challenge.
New methods may reveal where airborne spiders actually travel.
The journey links behavior, biology, and atmospheric physics. A wingless spider crosses the sky by combining silk, wind, and Earth's electric field.
Above powerful thunderstorms, enormous electrical flashes can appear where the atmosphere is already approaching the edge of space. These events occur far above ordinary weather. Across atmospheric layers most people never associate with lightning. Above storms, conventional lightning moves through clouds or toward ground, but other electrical disturbances illuminate the sky overhead, across altitude. At those heights, air density, pressure, and electrical breakdown behave very differently from conditions near Earth's surface. Thin air allows enormous luminous structures to develop from surprisingly small amounts of excited gas, above active storms. Excited nitrogen produces much of the characteristic red light seen in high-altitude sprites. Structure identifies mesospheric response. Most transient luminous events are faint, brief, and easiest to detect with sensitive cameras after darkness falls. A complete event may unfold within milliseconds, disappearing before an observer can consciously process its shape. Across altitude, high-speed imaging transforms one mysterious flash into a sequence of rapidly developing electrical structures. During brief flashes, the storm below can trigger light tens of kilometers above its cloud tops without a continuous visible bolt. Understanding the upper flash begins with how collisions inside thunderstorms separate electrical charge. This signal resolves storm charge. Violent collisions among ice and water particles help organize charge throughout a growing storm. Contrast tracks mesospheric response. Storm dynamics create large reservoirs of opposite charge separated across several kilometers of cloud. Boundary locates lightning coupling. As charge separation increases, the surrounding electric field strengthens throughout the cloud and nearby atmosphere during brief flashes. Lightning begins when electrical breakdown creates conductive channels through air that was previously insulating. Transition compares electrical breakdown.
Some sprite-producing flashes transfer positive charge from the cloud toward Earth in exceptionally powerful strokes. After lightning,
That rapidly changing field can push thin upper air beyond its local breakdown threshold. Emission exposes mesospheric response.
Red sites occupy the mesosphere and lower ionosphere, dramatically higher than thunderclouds or commercial aircraft, within thin air.
Their scale becomes clearer when placed above aircraft routes and below most orbiting spacecraft. Evidence frames sprite formation. A sprite can illuminate a region far larger than the storm feature that appears to trigger it. Enormous size does not imply long duration, because most visible sprite structure develops almost instantly, during brief flashes. Some sprites follow their parent stroke almost immediately, while others appear after a measurable delay, above active storms.
both rapid charge removal and continuing current can influence whether the upper atmosphere reaches breakdown within thin air.
Researchers use charge moment change to describe how strongly lightning alters the electric field above a storm.
Charge moment changes strongly increase the probability that a lightning flash produces a sprite across wide regions. Even powerful positive strokes do not guarantee sprites because atmospheric conductivity and storm geometry also matter within plasma. Sprite initiation depends on several interacting conditions rather than one simple lightning measurement. This boundary maps global occurrence. Nighttime conditions favor optical detection and change the electrical response of thin mesospheric air above active thunderstorms.
Solar radiation alters electron density, affecting how electric fields build and dissipate above storms. Contrast tracks charge transfer.
Many events are observed at night because their faint emissions would disappear against bright daylight across wide regions.
Observers often photograph sprites from distant clear skies rather than standing beneath the parent thunderstorm during brief flashes.
Distance can improve visibility by exposing the entire region above a storm's cloud shield. Transition compares global occurrence.
Sensitive imaging captures emissions too brief and dim for ordinary cameras under most conditions. Network supports upper fields.
Precise timing links each upper atmospheric event with candidate lightning activity inside the storm below, after powerful lightning. These matched observations establish the connection between sprites and powerful lightning charge transfers. This channel distinguishes storm geometry. Sprites occur worldwide wherever sufficiently energetic thunderstorms interact with favorable upper atmospheric conditions. They are not limited to tropical convection, although storm structures and triggering patterns can differ above active storms. Many sprites resemble luminous jellyfish, with a bright body suspended above long descending tendrils. Channel tests ionospheric change. Individual streamers propagate through localized electric fields and build the sprite's intricate lower structure. Evidence frames radio effects. Ionization grows around moving streamer tips, producing visible channels that divide repeatedly. This observed response measures ionospheric change. Different streamer polarities can develop in opposite directions within the same enormous event. This observation reveals halo development. Other events appear as simple luminous columns with little branching visible at ordinary video speed, within thin air. Sprites frequently occur in clusters distributed across a broad region above the parent storm. Observation records ionospheric change.
Successive sprites can appear to dance across the sky as lightning activity moves through the storm, across altitude.
Wind shear and tilted storm charge can shift sprites away from the parent ground stroke during brief flashes. The upper discharge may not sit directly above the point where lightning reaches the ground, above active storms.
A broad sprite halo sometimes appears before or without bright streamer development. This synchronized geometry reveals halo development.
Halos arise from diffuse electrical excitation rather than the narrow channels defining mature sprite streamers after powerful lightning.
Under suitable fields, a halo can transition into structured streamers that grow downward rapidly. Boundary locates ionospheric change.
Microsecond imaging reveals a developmental sequence hidden inside the brief visible flash. This measured sequence links streamer growth. Bright streamers can travel extraordinarily fast through the thin upper atmosphere. This field explains streamer growth above storms. The event extinguishes once local fields can no longer sustain ionization and energetic electron collisions within thin air. Although the light vanishes quickly, the upper atmosphere can remain electrically disturbed afterward. This sequence connects plasma motion.
Sprites and related events can produce measurable changes in very low frequency radio propagation. Emission exposes streamer growth.
Remote radio measurements help detect electrical disturbances even when clouds or distance block optical observations during brief flashes. Combined cameras, radio sensors, and lightning networks reveals how thunderstorms couple electrically with the upper atmosphere above them. Blue jets begin near storm tops and propagate upward through the stratosphere, rather than appearing suddenly far above. Unlike sprites, blue jets develop upward from the thunderstorm itself. This signal explains jet development within thin air. Typical blue jets terminate well below the highest sprite structures. This transition compares event rarity within thin air. Different colors reflect atmospheric density, composition, and the energies exciting nitrogen molecules. This mapped profile connects charge transport. Blue jet emissions arise from excited and ionized nitrogen within denser stratospheric air above thunderstorm cloud tops. Ion streamers combine into the luminous structure recorded by sensitive high-speed cameras, revealing jet development frame by frame. Some observed blue jets follow extremely brief electrical activity embedded within the cloud. This profile links plasma structure. Storm charge arrangement determines whether breakdown remains internal or escapes toward the stratosphere. This pattern tests global circuitry. Some upward discharges grow beyond ordinary blue jet altitudes and enter a different category. Response measures cloud escape. Gigantic jets can create a direct electrical connection between thunderstorms and the lower ionosphere. Profile connects jet development. Upper branches reach approximately the same height as the base of the ionosphere. Pattern distinguishes event rarity. A single gigantic jet can extend many times higher than the storm producing it. Contrast tracks plasma structure. High-speed observations show that gigantic jets can advance through repeated leader steps and streamer bursts. Across altitude, different plasma structures coexist within the same upward discharge. This response constrains cloud escape within the upper atmosphere. Most attempted branches terminate before reaching the ionosphere. This profile links jet development within the upper atmosphere. A discharge changes structure as air density and conductivity vary with altitude. This mapped evidence frames charge transport.
Observed gigantic jets can transfer substantial electrical charge directly upward. This response measures global circuitry within thin air.
Gigantic jets represent one visible pathway connecting storm electricity with the planet-wide atmospheric circuit across wide regions. These jets are uncommon relative to the enormous number of lightning flashes occurring worldwide. Trace constrains global circuitry. Limited observations still prevent a complete global climatology of gigantic jets, especially across remote tropical oceans and continents. Elves are enormous, faint rings produced when a lightning electromagnetic pulse strikes the lower ionosphere, within thin air. An ELVE can spread across a region hundreds of kilometers wide within a fraction of a millisecond. The parent lightning does not need to send a physical channel into the ring. Measurement maps historical discovery.
Magnetic energy briefly excites the lower ionosphere and creates the expanding optical emission. This observation reveals historical discovery.
Its geometry reflects the outward-moving electromagnetic pulse intersecting a thin atmospheric layer. This timing exposes sensor fusion. Most ELVs vanish within about a millisecond, making them among the fastest transient luminous events within thin air. Different event families occupy distinct timescales despite all being associated with thunderstorms. This synchronized boundary locates optical detection. Fast photometers aboard spacecraft are especially effective at detecting ELVs. This sequence links sensor fusion within thin air. Viewing from above removes cloud obstruction and reveals the event's true horizontal scale. This contrast frames ELV expansion. Repeated orbital observations help estimate occurrence rates beyond what ground cameras can measure. This boundary maps historical discovery.
The first confirmed sprite recording appeared accidentally during an unrelated nighttime camera test in July 1989.
Repeated viewing revealed that the strange flash was real rather than a camera artifact. Contrast tracks event timing.
Initial observations soon provided more examples and confirmed that the phenomenon extended across large storm systems, across altitude. Different perspectives revealed structures that looked confusing or incomplete from the ground. This brief sequence links event timing. Coordinated observations reconstruct altitude, size, and timing more accurately than any single camera. Researchers combine optical imagery with storm structure and electrical measurements to identify triggering conditions. Network supports sensor fusion.
Millisecond synchronization separates plausible parent flashes from unrelated lightning occurring nearby. This structure supports ELV expansion above storms.
Faster cameras expose plasma motion that ordinary video compresses into one featureless flash. This channel distinguishes optical detection. Spectroscopy identifies which molecular transitions generate each event's characteristic light. This pattern distinguishes historical discovery within thin air. Color and spectrum provide remote clues about otherwise inaccessible upper atmospheric conditions. This mapped structure identifies event timing. Space-based instruments now watch thunderstorms from above, where cloud tops cannot hide upward electrical activity after lightning.
ASIM combines imaging, fast light measurements, and high-energy detectors during repeated passes over active storms, above storms.
Orbital measurements captured blue jets beginning with extremely brief electrical activity inside cloud tops. Measurement maps forecast skill. Multi-channel observations distinguish genuine events from reflections, cosmic rays, and ordinary lightning glare. Field resolves ionospheric response.
From orbit, ELVs appear as complete rings rather than partial arcs hidden near the horizon, above active storms.
Astronaut photography complements automated instruments by targeting storms selected from forecasts and real-time observation within thin air.
Successful observations require predicting where intense storms will intersect a spacecraft's narrow viewing window. Observation records remaining uncertainty. Skilled citizen observers now contribute valuable images, timestamps, and storm locations to scientific databases. Timing clarifies sensor coordination. Multiple viewpoints can estimate altitude and structure, even when no dedicated instrument observed the event, during brief flashes.
Modern constructions reveal how upward leaders develop inside storms before escaping into the atmosphere. Profile connects ionospheric response.
Scientists investigate whether transient luminous events measurably alter chemistry throughout the middle atmosphere and lower ionosphere locally.
Individual events are dramatic visually, but their global chemical importance remains uncertain. This mapped emission exposes ionospheric response.
Electrical disturbances can outlast visible light and temporarily modify the lower ionosphere. This resolved trace constrains chemical effects.
Background atmospheric waves may influence where breakdown begins and how sprite structures develop. This geometry records remaining uncertainty. Upper atmosphere conditions change continuously, complicating prediction from lightning measurements alone. This field explains orbital monitoring above storms.
Future systems may combine charge transfer, storm geometry, and ionospheric conditions to forecast events. Network supports ionospheric response.
Key questions were made about why apparently similar thunderstorms produce entirely different upper atmospheric discharges. Emission exposes orbital monitoring. The field has moved from disputed sightings toward detailed physics, yet important parts of the system remain unexplained.
Thunderstorms do not end at the cloud top. Their electrical influence can reach the boundary between atmosphere and space.
The Great Pyramid still contains spaces whose purpose and exact shape remain unknown.
Khufu's monument belongs to a much larger royal landscape at Giza. Originally, polished limestone covered the stepped core visible today. Erosion and stone removal changed the monument's outer profile. Its builders established an exceptionally regular base.
The pyramid's orientation closely follows the cardinal directions.
Ancient surveyors had several possible methods for finding true north. The exact alignment procedure remains debated. The monument required quarrying, transport, and positioning on a massive scale. Egyptian crews relied on familiar materials, organized with extraordinary coordination. Much of the core limestone came from local quarries beside the pyramid. Workers isolated blocks by cutting trenches around them. Levers helped separate and reposition heavy stones. Sleds distributed weight across the ground. Moistening sand can reduce the force needed to pull a sled. Water transport moved selected stone closer to the plateau. High-quality casing limestone arrived from the Tura quarries. Granite for internal chambers traveled from southern Egypt. The river linked distant quarries with the building site.
The pyramid depended on transport infrastructure as much as stoneworking skill.
The known interior begins with a sloping passage entering from the north. Part of the route cuts directly through the plateau's limestone. The subterranean chamber was left incomplete.
Its intended function remains uncertain.
A concealed junction branches upward toward the pyramid's main chambers. This route was carefully built within the rising masonry.
The Grand Gallery is the pyramid's most dramatic known internal space. Its walls narrow upward through overlapping courses. Architectural details suggest specialized construction or closure procedures. No single explanation for the gallery's full role is universally accepted.
A separate passage leads to the chamber, traditionally called the Queen's Chamber.
No queen was found there, and the traditional name may mislead.
The niche's original purpose is unknown. Small channels extend upward from the chamber. Exploration found doors or blocking stones within the shafts.
Copper-like fittings increased curiosity without revealing the space beyond.
Robotic probes exposed another confined section, not a large treasure chamber.
The upper route passes through a complex granite antechamber. Granite barriers could seal the final chamber route. The king's chamber contains the monument's surviving stone sarcophagus. Above the chamber, stacked spaces redistribute enormous masonry loads. The upper roof channels pressure away from the chamber ceiling. Internal geometry was engineered to manage crushing forces.
Modern scans revealed a major unknown space above the Grand Gallery.
Its precise shape cannot yet be reconstructed. The detected zone extends for at least about 30 meters.
Muon data do not yet determine its orientation or internal divisions.
Its existence is better established than its architecture. Independent muon measurements confirmed the anomaly. Cosmic particles made the hidden space visible without drilling. Another scan detected a corridor behind the pyramid's north face chevrons.
The hidden corridor extends inward for roughly 9 meters.
Its destination and function remain uncertain. A miniature camera provided the first direct images inside.
The corridor has a gabled ceiling beneath the external chevrons. One possibility is that it protects masonry below from weight.
Structural and access-related functions are both discussed.
No confirmed doorway has been found at its end.
Additional methods have reinforced the corridor's location.
Multiple techniques now describe the same hidden structure.
No proven passage currently connects the two discoveries. The pyramid's interior mixes documented corridors with unresolved anomalies.
Different discoveries carry different levels of certainty.
Scientists distinguish physical entry from remote imaging.
Voids transmit more cosmic muons than dense masonry.
Large datasets convert particle counts into internal density images. Repeated measurements reduce the chance of a false signal. The big void remained visible across independent analyses. No evidence shows that the void contains treasure or a royal burial.
Its role may relate to construction, load management, or an unknown passage system. Understanding hidden spaces may reveal how the pyramid was assembled. Internal passages had to remain accessible during construction.
Temporary construction routes could later disappear inside the core.
No surviving plan identifies the complete ramp system.
A single straight ramp becomes increasingly massive at greater height. Straight ramps remain plausible for early construction stages. Switchback ramps reduce overall ramp length. External spirals could obstruct surveying of corners and faces.
Internal ramp models place some hauling routes within the structure. Archaeological confirmation for a complete internal spiral remains limited. Levers may have raised blocks through shorter vertical steps. Temporary supports could hold stones between lifts. Ropes coordinated pulling, steering, and braking. Simple direction-changing devices may have multiplied crew control. Builders probably used different methods at different stages. Material size and route requirements changed with height. Some internal granite elements demanded specialized handling.
The exact lifting sequence for massive granite remains debated. Construction traces constrain theories even when they do not settle them. No exotic technology is required by the archaeological evidence. Archaeology uncovered a substantial community supporting pyramid construction.
The settlement contained infrastructure for feeding and organizing labor.
Staple foods sustained large rotating work teams. Animal remains show substantial meat provisioning.
Some workers survived serious injuries with care.
Construction depended on organized crews rather than chained masses.
Specialized roles connected quarry, river, workshop, and monument.
Mera's log records limestone transport to Khufu's construction site. The diary describes repeated deliveries rather than legendary machinery.
The project mobilized